Good morning, everybody. So thank you so much for the introduction, and thank you, NREC, for this opportunity to present our research, all the support to our projects. So now I see how the agenda of this morning is being developed. Right? We have watershed scale kind of presentations in between of those field scale work. So I hope you don't mind that we will move on to the watershed scale again, but our research is a bit different than Bing's work just presented earlier. Our focus is largely at the local watershed scale. So we call it the Black Slough Watershed Project. So actually this work is largely motivated by success at the field scale. So these are long-term projects funded by NREC and led by Lowell Gentry. So I'm sure you will learn from Lowell just about the details of these projects just in a moment. But the key finding from these projects, which is relevant to our current project, is that moving for fertilizer application to spring reduce tile nitrate load by 19 to 33%. And on top of that, if we combine cereal rye cover crop and the spring nitrogen application, that can increase the reduction the percentage to up to 43%. So then basically the research question of this project is to find out if we adopt these kind of conservation work at the watershed scale, how much reduction we can see over a relatively short time period. I'm talking about a few years because any project has time limitations. So we're really looking at short-term impact, not long-term effects. And also we're curious, is it possible there can be time lags between implementing those conservation practices and seeing measurable reduction outcomes? I think this is quite important because even for our field scale work, we didn't see clear signal right away after implementing those practices. It was not until years 2, year 3 that we start to see clear trend that nutrient loads is going down. So I think a clear answer to this second question will help us to better set a bar for expectation for the first question, just how much reduction we can achieve over a short term. So this is our study area, the upper Embar River watershed. So it's, if you look at the upper right corner, the reddish color, that's our campus. So it's not very far away from what we are here right now. So it's about 20, maybe 25 minutes driving. So it's a pretty large river. So it's a fourth order river. So as see, the picture down there, the watershed area is about 48,000 hectares. So very similar to many, many other watersheds in this region. It's very flat. It's predominantly corn and soybean, intensively tile drained. So, but if you move to the lower portion of this watershed, right? So I'm not sure if you can see my cursor moving, but if you move to the lower part of the watershed, you do see some kind of mixed land use there. Some wetlands there, some developed lands there, some riparian forest there, like I show in the photo here. So within this watershed, we have we call it experimental watershed Black Slough. So Black Slough is about 5.8% by area compared to the larger watershed. It contains 6,500 acres agricultural land, which includes 190 parcels, 140 farmlands, and based on our long-term working experience in this region, most of the farmers living within Black Slough use full nitrogen application, and the tillage is largely conventional. And before the start of this project, there was very, very limited amount of winter cover crop within this small watershed. And by the way, this is we call a headwater watershed, receiving a lot of tile drainage directly. So we have 26 years of sub-weekly nitrate concentration at both locations, Black Slough and the upper Embar River. So that's what I show. If you look at on the left, that's concentration from those two locations over time. This was started in 1999. I think it's collected by Lowell Gentry in the back. So we're still doing this day. I think our groups do that every Monday, I guess, yesterday. So we call it sub-weekly because at least we get one sample from those two locations every week. I guess, except the Christmas holiday break. But more likely during those spring high flow events, we will go out on multiple days in a row just to try to catch the high flow, because that's the period matter the most. So on the right, you can see if you plot the concentration together, kind of collected and measured at the same time, they almost follow a perfect linear relationship, right? If you can see you fit a line through it, R squared is like 0.9. So, but the next thing is concentration is not enough. We also need to know how much water is leaving these watersheds. Then you can combine them to calculate we call loads, right? So that's why we installed a stream gauge at the Black Slough in late 2023. And then for since 2024, we have continuous 15-minute data for stream flow from Black Slough. But the issue here is we do not have the stream flow data for the historical period. That's from 1999 to 2023. But fortunately, if you compare data collected at the smaller watershed, the Black Slough, and the bigger watershed, Upper Imba River, their stream flow always follow a very, very similar dynamics, meaning that we can use the data collected downstream at the Upper Imba River, which is available since 1970s, and we can use that to predict the stream flow at Black Slough. That's essentially, I'm showing right here. If you look at the plot, the black line is the measured Black Slough stream flow, and the red one is the predicted using the downstream Upper Imba River stream flow. So using this prediction model, then we can predict stream flow leaving Black Slough for the entire period. That's what I show at the bottom from 1999 to 2023, right? So now we have concentrations, we have stream flow for this long 26 period. Then we can calculate load. So that's what I show on this figure there. So on this figure, I have the Upper Imba River annual load as our x, our horizontal. For the vertical is the Black Slough annual load. So each dot is for 1 year, and the arrow bars surrounding each dot is accounting for the uncertainty in the prediction of stream flow Black Slough. So you can see they follow almost perfect linear relationship here, right? So the dashed line give you 1-to-1 relationship. If you, again, fit a line through those, they're almost perfect. So which kind of not surprising because they always have similar concentrations and similar kind of dynamics in stream flow. So the idea here is now we can use the smaller watershed Black Slough as our experimental watershed, the test bed. Let's see, we do conservation there and do as much as we can to increase coverage of cover crop and fertilizer timing change, how much reduction we can achieve, compared to the bigger watershed, right? So mathematically, if those conservation work really work at the smaller the Black Slough, we would expect to see, again, if you can see my cursor moving, this dot fall off the linear relationship, right? Because Black Slough is so small, what we do within Black Slough actually has basically nothing to do with the Upper Imba River because it's much bigger. And mathematically, we can calculate something called counterfactual load, or our expectation for Black Slough for any given year based on what we measure at the bigger watershed, right? From there, we can calculate reduction load for a given year. So this basically, we call this baseline data over this 26 years, and that really the foundation of this project. Just to help you better understand this concept, I want to give you an analogy because this is so important. I always think these two watersheds like big brother versus little brother, right? So if you have kids, the little one always tend to follow the bigger one, kind of mimic what they're doing. It kind of makes sense because they're raised within the same environment and treated in similar ways. So in our case, we have been observing these two brothers for 26 years. So we know exactly what is doing if we, by looking at what the other is doing, right? So in this case, we are trying to do management on the little brother to see any change we can achieve when compare that to the big brother. So that's essentially we are doing right here. So now I want to share you some results from just year 1 of this project. So we started farmer recruitment in September 2024. This is led by Dan Schaefer. I know Dan is not here today, but shout out to Dan because he knows everyone living in Black Slough. He called everybody and did the contract, sign up for everybody. So we can't really go anywhere without Dan's leadership on this project. So, and then we pay $40 per acre for both treatments, moving fertilizer for application to spring, and also plant cover crop ahead of soybean. So we recommended cover crop kind of planting dates, termination dates, but other than that, we had no other mandates on how people would like to farm their fields. Other than if you sign up for timing change, you cannot apply fertilizer before March the 1st. So for this first year, we have about 2,200 acres enrolled in this project, but most of them are for fertilizer timing change. That's the ones shaded in orange color on this map. We only have about 400 acres plus for cover crop, and also 170 acres that kind of signed up for both treatments. So if you look at this map, those shaded in green is for cover crop. So the cover crop coverage for year 1 is only about 8%, right, of the total agricultural land within the Black Slough watershed. So we installed continuous nitrate sensors at those 2 locations. That's what I show right here. So that's how we keep monitoring these 2 watersheds. So for their nitrate concentration, for basically every minute, there is no single event is being escaped by this effort for monitoring load and the stream flow. So, and also on here, you see those kind of dots for weekly samples, and then we collect every week, so we can compare the sensor performance and also grab samples. On top of that, we also do a lot of field work because we just don't want to, keep all the attention on the watershed scale, but we actually care how those practices change soil properties and also change tail drainage concentrations. So we collect 10 tail drainage outlets within the Black Slough watersheds on a weekly basis. We sample every bridge along the Black Slough, also on a weekly basis for nitrate, for phosphorus. We sample 6 paired fields within Black Slough for topsoil, for a whole bunch of soil health properties. And also for all those fields signed up and participate in this project for the cover crop treatment, we sample their field to measure the above ground nitrogen biomass basically collected in those cover crop biomass. So here's some results from, again, year 1 for the cover crop treatment. We have 5 fields using this treatment for year 1, and 4 of them use the cereal rye, and we found across the entire non-growing season, the above-ground nitrogen biomass uptake ranged from 20 pounds nitrogen per acre up to 50 pounds nitrogen per acre. We also had a field using winter cover crop, so which gave us almost 150 pounds nitrogen per acre in above-ground uptake. So I do want to clarify a little bit, because for this particular farm, they fertilize the winter wheat using manure, and then harvest the winter wheat to feed their cows. Because both activities happening within the watershed, we still count winter wheat here as a catch crop, right? And then you add them all together and normalize the watershed area, we have 2.5 pounds nitrogen per acre when upscaled to the entire Black Slough watershed, which represent 11% of its long-term mean annual load from this watershed. So here's some tile drainage nitrate concentrations across different individual outlets. The take-home message here is we see a lot of variability. So for example, if you go for this plot, you go from left to right, we have tile drainage from those fields with cover crops, with fertilizer timing change, with both treatments, with no treatment, which can be a baseline, right? And also external sources. We also have drainage pipes kind of from we don't really know where they're coming from, the water, but basically discharge into the Black Slough stream, and also, of course, all the bridges and the outlet at the Black Slough. Again, the take-home message here is it's very variable for its concentration. For example, if you look at those fertilizer timing change, they actually have one of the highest nitrate concentration at their tile outlets. But the issue here is we don't have any baseline data for these farms, right? That's kind of the challenge for working in real world kind of farming land. We don't have baseline data, but that's not an issue for our watershed scale. We do have 26 years of baseline. So the hope here is we just continuous measuring the concentrations, and hopefully we can see some trend and pattern when we come to year 2 or year 3. So now I'm here showing the concentration we measure at Black Slough. I know it's a busy plot there, but just let me walk you through the individual components here. So first of all, those the shaded envelope in the back, right? That's the maximum and minimum concentration for each day of the year over that baseline condition from 1999 to 2023. So this is organized as a water year. A water year starts at October the 1st, ends the end of September, right? So it's very clear for this envelope, we had low concentration during summer and fall, but highest concentration during spring and kind of around May. And then for the blue line, that's for our sensor at the Black Slough watershed. So this is actually collected in 2024. Our study started in 2025. So we call it year 0. That's just before the treatment happened in our watershed. So 2024 water year is a relatively wet year. If you look at the discharge, it's around 40% percentile or 50 percentile. So for the nitrate concentration, it's also basically within the medium or kind of average concentration for this baseline condition. And then move on to the red line here. That's after the treatment, right? That's for water year 2025. You see concentrations are lower there, right? Very clearly. But I can also tell you that that's one of the driest year in the past 3 decades. So the stream flow is at 12th percentile within that 30 years. So it's kind of clear right here. Now I'm comparing the Upper Amba River and the Black Slough on this plot. So Upper Amba River, that's the upper part, is in blue, and the Black Slough is in red. And also I show discharge or stream flow measured in Black Slough at the bottom. So again, you can see for year 0, again, 2024, you see multiple events. It's a relatively wet year. A lot of, it's very flashy for the concentration at both locations, but Black Slough always kind of peak sooner and also higher compared to Upper Amba River. And then move on to year 1. That's our first year of this project. Just only maybe 2 or 3 large events happened within this year. But if you look at concentrations there, seems like during spring, right? That's after April, the concentrations were similar between those 2 sites, which seems to be promising and showing some reduction effect. But I can tell you that the dryness play a really large role here in those concentrations. So just take those concentrations into kind of the context of the historical period. What I show here is annual loads for the entire period from 1999, and the flow weighted mean concentration on the right, again, for the same period. The dots being highlighted there is our year 1, just after the treatment. So for loads, we saw basically one of the lowest during the last 30 years. And for concentration here, actually it's interesting, we found a declining trend starting in 2015, and then seems there is a reversal of concentration for both locations. So my student, Carlos Guacho, had a poster. We conducted some analysis like being talked about earlier, so to look at hydrology and management for these 2 locations, and he can tell you more about those details. So now we can place those measured concentration and into the historical context, right, to see how good we are for year 1. So Actually, I want to start with year 0. If you're now looking at this plot, right, the red one is the year 0, 2024. It's actually lie above that line, meaning that Black Slough actually contributed nitrate load higher than it did in the past for the historical period. And for year 1, that's our first year of this project, first of all, it basically very low toward the end of this kind of the range of loads we saw in the past, and it right on the the linear relationship. So now you can plug in those measured loads from those 2 locations to calculate percentage reduction. We had 8.9 pounds nitrogen per acre for Black Slough. We have 9.7 pounds nitrogen per acre for Upper Emba River. And that means we had 0.6 plus minus 2.4%. So basically no reduction, right? I'm not sure how this results came across to you, but that's what we saw for year 1. So now I'm gonna switch gears real quick and just talk about what we have been doing for addressing second question. Remember, the time delay between the implementation and the emergence of reduction sign. So the approach we use for addressing this question is measuring isotope tracers, all right? So you may heard something like carbon-14 for dating the age of rocks or dinosaurs. So in our case, we use kind of similar concept. It's not exactly the same, similar. But in this case, we measure the oxygen isotopes in water. So we measure oxygen 18. That's the one I show on the upper kind of right corner. So oxygen 18 actually contain really, really small amount. Kind of if you look at the natural abundance of oxygen atoms, it only account for 0.2%. So we have been measuring the oxygen isotopes, oxygen 18 in rainwater within the Upper Emba River watershed using the simple devices like this. So if you look at the plot over there, the red dots are concentration. That's the isotopes, oxygen isotopes in rainwater from 2022. Right? So you see clear seasonal patterns there. This is because during the summertime, we receive moisture from the Gulf region, and during winter time, we receive moisture from the polar region, and they have very different isotope signals, right? So that's basically the foundation for using this technology. So now let me just walk you through very quickly a thought experiment, how we can kind of leverage this natural abundance isotopes to study legacy effect or water age. So think about this. So over the entire year, you set out a bucket, right? That's the first example on top. Set out this bucket and try to measure the water outflow from the bucket. That's just the water spill out of the bucket, right? So then we know that in the precipitation, it has a seasonal patterns in water isotopes. We would expect to see kind of similar trend for the outflow from that bucket, because there's not much water in it. You may see a little bit dampening, right? That's what I show right here. That's the blue line is the isotope or precipitation. The red is bucket outflow. Maybe you see a little bit dampening, but that's due to water within the bucket that kind of average out the precipitation signal. But then if you think of a swimming pool, right? You have significantly more water. That's the second scenario I show on the bottom. Now, if you try to measure the outflow from the the swimming pool, the dampening is much bigger compared to a bucket because you have much more water in a swimming pool. And also you will see kind of the peak of those seasonal patterns will get shifted because again, due to the averaging of water already in that swimming pool that average out the precipitation signal. Basically, that's how we can track water for its age, for its identity, when it comes to this system. So now I'm gonna show you our results, from those 2 watersheds, right? We collected stream water samples and measure water isotopes every day. So we have a daily sample coming for water isotope analysis. So the one at the bottom, so the longest one, right? Again, this one right here, that's the comparison of precipitation, which is the red dots, and black dots is the water isotopes in stream flow in Upper Amba River. And the top one is for Black Slough. So comparing those two kind of patterns, you do see that the Upper Amba River has kind of quite a few responses over time. If you focus here, it has those peaks or troughs correlated to precipitation water, right? So meaning that it's responsive to those precipitation input. But if you look at Black Slough, it's almost like a flat line, right? Really flat. So back to the previous thought experiment, that meaning a very well mixing a lot of water stored in this system. We also have, collected tile drainage samples and also groundwater samples. They all look flat, meaning that a lot of mixing, a lot of water there, and Black Slough look a lot more like those tile drainage and groundwater compared to the bigger watershed. And we also can, make it a little bit more quantitative. We can calculate some, we call it young water, that's just water coming in within the last 2 to 3 months. It accounts for 24%, a quarter of the total annual stream flow at the Upper Amba River, but only 4% in Black Slough. So again, that means there can be some strong time lag at the Black Slough watershed. So that kind of interesting results, and also honestly a bit surprising to us, because we thought Black Slough is smaller, it should be more responsive, but that just dropped me into this kind of the background of Black Slough a little bit more. So, I'm not native English speaker, right, obviously, but I have heard people call Black Slough or Black Slough. I really don't know how to say this for you English people here. So that's a question to you, but I then Googled it and ChatGPT'd it, and to better understand what does it mean slough, right? Why it's not a Greek, why it's not a string. So that's what I found. So the initial settlers use, I still know how to say it, sorry, to describe sluggish streams in muddy or swampy places, right? So that's kind of indication about the hydrogeology of this region. It could be, a really high groundwater table, relatively shallow, the limiting layer below ground, that just causes a very good mixing of water in this watershed, right? So that means a lot of old water there, but I want to be clear, that does not necessarily mean strong legacy effect, because you can have old water but contain no nitrogen, right? That's something we are currently looking at, the combining those tracers and modeling to better study the time lag for nitrogen output. So just very quickly to kind of summarize, we conducted a field day on August 14, 2025 within the Black Slough watershed, just to get everybody together, talk about the project, show our results, and also engage more people to join us for this effort. And I think largely, due to that kind of outreach effort, our coverage really went up for the second year, right? So for this second year, we had more than half of the watershed going through either one of those two treatments. And we have more than, I think this is 900 acres for cover crop. On top of that, we have 400 acres for both treatments, meaning that 1,400 acres for cover crops, which account for 20% of the total agricultural lands within this watershed. So again, our preliminary results for year one, we did not see significant reduction in year one, but I need to be clear that we only had 1/3 of the watershed undergoing sun treatment, and it's an exceptionally dry year for this first year. In year two, we'll provide a much stronger test of the concept. Hopefully we can get more rains this year. So, and also we see limited young water contribution to stream flow, especially in Black Slough, likely reflecting a strong water mixing, high groundwater table, but the magnitude of legacy effect depends on a lot of other processes. That's something we're currently looking at for this project. So, thank you.
Thank you, Dr. Yu.
Do you have
Thank you.
time for question?